One type of situation that happens a lot in applications is when you have one quantity that depends on another quantity. So the first quantity is a function of the second quantity, and then that second quantity is a function of a third quantity. It depends on a third quantity. So if we call the first quantity f, the second one g, and the third one x, then g is a function of x and f is a function of g. So when you put it all together, you've got f is a function of g is a function of x. So you've got one function sitting inside of another function. And the technical language that people use for this is you've got a composition of functions. And now my question is, if I've got a composition of functions like this, how can I find the rate of change of the first quantity, the f, in terms of that third quantity, the x? How fast is it changing with respect to x? If I wanted to just take a guess at this, I would think, well, maybe I could just take the derivative of f and then take the derivative of g, since this is f of g. Take the derivative of f, take the derivative of g, and then stick the derivative of g inside the derivative of f. And that may work. If you've taken guesses, intuitive guesses like this for the product rule and the quotient rule, then you may be skeptical about my guess here. But let's just see if it works. Let's use a simple example. Let's use an inside function g of x as x cubed, and then let's use an outside function f of g to be just g squared. So then we've got f of g of x equals x cubed in parentheses squared. If we follow my guess, then since f is just g squared, the derivative of that is 2 times g. And then g was x cubed, the derivative of that is 3x squared. So if I take the 2g and I put the 3x squared in for the g, I get 2 times in parentheses 3x squared, which gives me 6x squared. And then I have to ask, is that the correct derivative? If it is, then maybe I've got the right rule. If it's not, then I definitely don't have the right rule. So the real derivative is we look at x cubed squared, and we know that that's just x to the 6th. We use the power rule, we get 6x to the 5th. So the derivative that we got with my guess is wrong. I'm going to have to do something else to figure out what the pattern is, what the rule is, if there is one, for a composition of functions like this. It turns out that it's actually fairly simple. So let's take a look at it. If I want the derivative of this composition, what I'm really asking is, what's the rate of change of f with respect to x? So I want df dx. And the definition, or the method of increments, says that's the limit as delta x goes to 0 of delta f over delta x. Remember, these deltas just mean change, so change in f over change in x. And you notice that there's no g's in this formula so far. That g is my sort of the middle variable. I want to get that in somehow. So I'm going to take that change in f over change in x, and I'm going to multiply it by change in g over change in g. So I'm really just multiplying by 1. I'm not changing anything, but that slips in the change in g, and that might help me to get somewhere. And now if you look at this and think about it for a second, you can rearrange this so that something nice pops out of it. If you take the change in f over change in x and you multiply by change in g over change in g, then you can switch the two denominators. When you multiply fractions, you multiply straight across, and it doesn't matter the order in which we multiply those. So let's bring the change in g on the bottom over underneath the change in f, and move that change in x over underneath the change in g. And now when we take the limit as change in x goes to 0 of this product, we're really just letting change in x go to 0 for each piece of the product. So we can rewrite it like this. And now you see that that second limit is just the derivative of g with respect to x. So that part is nice. It's taken care of. This first limit is almost the derivative of f with respect to g, but it looks a little different. If it was the derivative of f with respect to g, then we would be taking the limit as the change in g goes to 0, not the change in x. So my question is, if we let the change in x go to 0 like this, does that make the change in g also go to 0? If it does, then this first limit is really just the limit as change in g goes to 0, and then that is the derivative of f with respect to g. So what do you think? If we let change in x go to 0, then does that make the change in g go to 0? Well, it depends on what kind of function it is, but we're assuming that we can take the derivative of g. And in fact, every function that you know of is continuous on its domain. So as long as x is in the domain of g, then the derivative of g will exist there. The only simple exceptions to that are functions that you define in terms of pieces. So if you've got that, then it's slightly more complicated, but that's not what we're going to be working with most of the time, so I'm not going to worry about that. If the function is continuous, then by definition that means that as change in x goes to 0, change in g also goes to 0. If you're a little rusty on that, you can see my video on continuity. It's a fairly simple concept. It's pretty intuitive. So this change in x going to 0 really does mean the change in g is going to 0. So this really is just the derivative of f with respect to g, and that gives us the formula. It's pretty nice and simple. It's just the derivative of f with respect to g times the derivative of g with respect to x. So the derivative of a composition of functions is just the product of the two derivatives. And just to make sure that this really works on something simple, let's go back to the example we had before where g was x cubed and f was g squared. Then if we try this pattern out, this rule that we just developed, it says the derivative of f with respect to x is first derivative of f with respect to g, so that's 2 times g, and then times derivative of g with respect to x, that's 3x squared. So we've got 2 times g times 3x squared. And then this g, we need to go back and fill in what g is. G is x cubed. So we've got 2x cubed times 3x squared. That gives us 6x to the 5th, which is the derivative of x to the 6th. So that's an indication that what we did really works. And it does. This is the correct rule. This is called the chain rule. And I think the reason that it's called the chain rule is because, remember, we had one quantity that depends on a second quantity, and then that second quantity depended on a third quantity. Well, we could have a situation, and it comes up plenty, where you have the third one depends on a fourth one, the fourth one depends on a fifth one, and so on. And so you've got sort of a chain of functions there. And when you do the derivative of this long chain, it turns out to just be the product of all the individual derivatives. So it's super nice rule, very useful chain rule.